In the last video, we saw that we start with a set, then we take a sigma algebra script f over S, and mu is a function from script f to 0, infinity is included, which is a measure. Now this triple, always written in this order, S, script f, mu, is called a measure space. But if we consider only these two things, this pair is called a measurable space. Now the term measurable occurs in three different contexts in measure theory, and today's lecture will be devoted to the term measurable. The first usage is this: I have a set and a sigma algebra over it. This pair, always written in this order, first the set then the sigma algebra, is called a measurable space. So this is something on which you can define a measure. So even before I talk about a measure, we have to take a measurable space. The second use is, if I give you a subset A of S, we call it measurable if that A is an element of script F. So all the elements of script F are subsets of S. These are kind of special subsets which we call measurable subsets. If we are working with probability measure, in that case measurable has a different synonym. We call a measurable set an event. For the third usage of the term measurable, we have to start with two measurable spaces, S script F and T script G. So S is some set, T is some other set. Here is a sigma algebra over S, here is a sigma algebra over T. Now we consider a function from this to this. So we take a function from S to T, just the two sets. We call this function measurable if for all B in script G, that is all measurable set here, its pre-image is measurable here. Now, just because I am using F inverse notation, this does not mean that F is 1 to 1 or anything. I will quickly remind you what is the definition of F inverse B. F inverse B denotes the set of all x in A such that Fx is in B. So whenever you take any measurable set, a subset of T, its pre-image, this is called the pre-image of B under F, is measurable in S. Now this definition, as well as the definition of a set being measurable if and only if it belongs to script F, they may be understood in an intuitive way, and I am going to discuss that now. Suppose I give you this set S, which has got three elements, apple, banana and candy, and I give you three statements. The first is, I love one of these, I do not love apple, I do not love candy. So just imagine that you are something like a computer program in which you are fed these three statements. Based on this, I ask you the question, do I love banana? So I give you this statement and I ask you, is this true? So this is my database. Based on that, I want you to tell me the truth or falsity of this. And you can say, yes, this must be true. If all these things are true, this will be true. Now imagine, can a computer program do this blindly? No, because these are three sentences and this is a completely different sentence. So it can look up all these things and still cannot figure out what to do because it can only look up. If the statement that you have asked is precisely one of these, in that case it can answer yes. If it is just the negation of this, then it can say no. But this is a completely different thing. There is no statement about banana here. But we human beings can conclude. We can infer more information given certain basic information. And the rules that we use to derive new informations are these three basic things: not, and or. And these correspond to complementation, intersection and union. Now I can say that these are actually various sets. I love one of these, that is the entire set. I do not love apple, so it is basically a complement. I do not love candy, that is C complement, and all these things are AND. So it is in S and A complement and C complement, and that is basically your B. So if these three statements are there, this complement and intersection, etc., will give me this also. And that is precisely the way we generate a sigma algebra from certain sets. So you can think of the fact that a given collection of sets generates a sigma algebra, means the sigma algebra gives you the totality of all information that you can derive from the given statements. So I gave you only S, A complement and C complement. You constructed, for example, out of that you constructed B. If I ask you the question, I love apple, true or false? That is A. You can say that, well, if A complement is true, A must be false. So all the things that you can construct out of the given things using union, intersection and complementation, they constitute the totality of information, and that is what we are calling sigma algebra. At yet another example, suppose I give you this information, my age is less than or equal to 50. And from this I ask the question, is my age greater than 60? Yes. You can immediately say that the answer will be no. So you can definitely say that the answer is no. Is my age less than 30? You are undecided. Based on this, you cannot answer this question. But if I ask my age is greater than 50, you can again answer no. Okay, now suppose I tell you that this is false. So earlier I said that this is true. Now I tell you this is false. And let us see whether you can answer all these questions. If I tell you this is false, can you be sure about this? Well, now you cannot be sure. So now you are unsure. What about this? If this is false, now you can be sure about this, that my age must be greater than 50, so it cannot be less than 30. Now you are sure. But in this case, you can be sure. So if it is false, you are sure that it is correct. So I will say that these two questions cannot always be answered unequivocally based on this information. When I say this information, I mean whether I tell you that this is true or this is false. Can you always answer these questions as either true or false? For this question, however, if I tell you it is true, you can immediately answer this. If I tell you it is false, you can immediately answer this. So I shall say this question is measurable with respect to this question, with respect to this fact. You understand why I am calling it measurable. So based on this, you can always infer the truth or falsity of this statement. But these two statements, you could be sure about this in certain cases. If it is true, then you can be sure. If it is false, then you can be sure. But you cannot be always sure. So these are not measurable and this is measurable. Now if you think for some time, you will understand that the definition that I had given you earlier in terms of sigma algebra and this, they are actually equivalent. Similarly, when I have a measurable space here, another measurable space here, and I give you a function and say that it is measurable, I actually mean the following thing. Suppose you give me, for every set, so you give me a point. So here there is a point. But I am not going to tell you what the point is. What I will do is that for every set in script f, I will tell you whether the point x belongs to that set or it does not belong to the set. So for every a in script f, I will tell you whether x belongs to a or it does not belong to a. Based on just this information, can you tell me for certain whether f of x, which is somewhere here, belongs to different sets of script G or not? So if I give you any set in script G, you should be able to tell me for sure if fx belongs to B or not. So I have not told you what x is. If I tell you what x is, you will compute fx and check. I have not told you x, but I have told you that my x belongs to this A, it does not belong to that set, So I tell you all these sets for this script f. Based on just that, can you tell me whether fx will belong to each of these sets? Yes or no? Let me give you a concrete example. But since this video is getting long, I will stop here. In the next video, I will give you a concrete example.